Okay, first speaker is Jörgen, and Jörgen, the stage is yours.
Thank you very much. Thank you for inviting me to this conference, which I have enjoyed for many years when I've been there present in Stony Brook. I miss that now, but I think this is a very good substitute, what we have. So I thought I would talk about an imaginary meeting between two people, John Nash, who was at Stony Brook several times, and Immanuel Kant, who was much earlier than us guys. As you know, Kant was thinking about different things, the reason, actually pure reason, but also, if you like, pure morality. And that sounds very alien to the way we think in economics. We are very consequentialistic usually, while that was a deontological theory. And I studied philosophy when I was young, alongside mathematics and physics. And then I wondered, would I ever see Immanuel Kant or anything like that anymore? And I thought, no. And suddenly he popped up in the dress of some equations in some stability conditions I was working on with Ingela earlier. So I will talk about that theme, but a little bit philosophically and from different angles. So just recalling how John Nash phrased his idea in his first paper in PNAs, 1950, he thought of individuals living rather individualistically, and everybody was there independently, not like John von Neumann thought in forming groups and coalitions, but walking around there and choosing from a set of strategies what to do. And then he evaluated what people did in terms of what he calls payments. I think in the earlier literature, most of the time we thought of these were kind of monetary payments or something like that. But as we know now, and if one reads Nash, this can be any real valued function really, which maps strategic profiles into real numbers. So we can allow for people who are altruistic or evil or whatever. Now that is his view, and then he thought, that people are individuals and they strive to do what is maximize whatever their payment is. If we then turn to Immanuel Kant, who wrote a book on the metaphysics of morals just before the French Revolution, he would say something like this in English, that act only according to that maxim whereby you can at the same time will that it become a universal law. So it's more like asking yourself, what is my duty or the right thing for me to do, or anybody in my situation when I'm there. And I guess we humans, we have both of these kinds of thoughts in our minds when we do things. We think of them both, what is to my benefit and also what would be the right thing to do now. And the question is then, can one reconcile them? Can we, or are they so different that we cannot really think of them in the same framework? And that's a challenge I will now raise. Okay, so Nash is individualistic and consequentialistic. So you think in terms of the consequences. Kant is universalistic. He says, what would be the good thing for somebody in my situation to do, not only me. And he's also deontological. So what is the right thing to do if people were doing what I'm doing now and in my situation? And that is not a consequentialistic principle. It can be connected with consequentialism, which I will do, but it's quite different. So it doesn't care about actually what is the advantage for me or anybody else, or what are the consequences for other people. It just asks what is the right thing to do. Now, his lead example, Kant's lead example, was actually kind of economics. It's like, sounds like behavioral economics, like experiments that people do now. So he asked himself the question, well, suppose I'm in distress. Is it okay to make a promise to somebody else with the intention not to keep it? So I ask for help and then, I pay back something or something. His answer is that the shortest way to discover whether a lying promise is consistent with duty is to ask myself if I would be able to say to myself, everyone may make a deceitful promise when he finds himself in a difficulty from which he cannot otherwise extricate himself. Well, while I cannot, maybe I can will the lie, I might need the money or help, I can by no means will that lying should be a universal law, for with such a law there would be no promises at all. Hence, my maxim, as soon as it should be made universal law, would necessarily destroy itself. So this couldn't be the right thing to do. And note here that it's deontological, so it's asked in principle. Also, it is actually not thinking about what it costs for me or for others or things like that. It's asked, is this something I could suggest should be a general rule for people? Now, That's a very different way of reasoning. And can one then relate these to each other? So that will depend then, to a large extent, I think, what meaning we attach to what Nash calls payment. Of course, there is an alternative route which says we shouldn't use Nash equilibrium. We should use some other equilibrium concept or some solution concept more in Kantian style. And that is what John Romer actually is working on, right? I stay with Nash as an approach for decision making in a strategic interaction, but allow for the possibility of moral reasoning. So one possibility, and that is what I will pursue here, is to consider symmetric games and use Nash equilibrium or some refinement thereof as a solution concept. So we stay within the paradigm of game theory, non-cooperative game theory. And with a pure Kantian player, I would think of a guy whose payment, in citation marks, would be defined in terms of the material consequences for the players involved if the other player who you meet and interact with, or the other players, if there are multiple players, would use the same strategy as you use. So this need not be two-player interactions, it could be n player. Then what would happen if all the others that I meet do what I'm doing now? Is that the right thing in a symmetric situation? If the interaction is asymmetric, it's harder to say what this means, the paradigm of Kant, because I cannot think of others choosing, what would it mean that others would choose what I'm doing in this interaction if they have a different strategy set. I think one way to reason in such asymmetric situation is to put oneself behind a veil of ignorance and saying, suppose I can be assigned any one of the roles of the game, and then the strategy will be kind of a meta strategy, what I would do in the different roles. I will not go into that now, however. So I will just presume we have a symmetric game, whether it's defined that way or not. Now, let's look at Kant's little game there, promise game. I rewrote this in words, not a game tree, but it's easy to draw a little game tree. So imagine now Kant's story with the guy being in distress. So I would think of it as follows. So nature flips a fair coin, and then if heads comes up, then player one falls in distress. And if tail comes up, then it's player two. And then they meet. And the distressed player may or may not ask for a loan with a payback promise, I presume, from the other player. And the other player may or may not give the loan then. And if the loan is given, then the guy who got the money or the help may or may not pay it back to the loan giver. So the loan taker may honor it or not. Now, one can associate, of course, payoffs or utilities to this, but I will distinguish between what I call material payoffs, which we define in terms of material consequences for these guys, and in order to distinguish them from utilities, which might involve moral considerations. So not to confound them, I call them material payoffs, and we could then say that the guy who falls in distress has a -1, is distressed, if no loan is given, and suppose the other guy lends the money but it's not paid back, then I suppose he falls to 0, so it's a bit higher, he's not as badly off. And then I imagine that 1 is the payoff to the distressed player if the loan is given, so he's increased from -1 to 1, so lifted up by 2, and let 2 be the benchmark, the material payoff to player 2 if nothing happens, if he's not giving the loan, or if the loan is given and paid back. So he's indifferent between giving it or not giving it at all. So player 1, if paying back, gives him some compensation in some way. So 2 feels fine. Now, if we would apply Nash equilibrium or game theory to this, non-cooperative game theory, then we wouldn't get any loans, right? Because we would then define payment to a strategy X, in say behavior strategy or pure strategy, what you like, when you use strategy Y as the own material payoff to that guy. And then the guy who, if you give a loan, get the loan, you don't pay it back. So on the path of a strategy profile, if it's Nash, you don't pay it back, and therefore there's no loan. So both end up in the situation without helping each other. So the expected payoff in material terms will be 1/2. Either I get -1, I'm in distress, or I get 2 if I'm the lucky guy, and the equal probability. So that is what is the expected material payoff. Now, what would Kant say? I imagine that he would say this. Maybe he would disagree with me. That I cannot verify. I would say that why don't we define payment now to any strategy X when used against strategy Y in this meta game where we think of, first nature tosses a coin, and then I should do this if I'm the guy in distress, and I should do such and such if I'm the guy who's not in distress. So in this symmetric game, then a payment I suggest to strategy X should be defined whenever it's used against some strategy Y as my own material payoff, if also the other player would use the same strategy. So in the ex ante situation, he would think the same way. It will be also the payoff to the other guy, of course, in this meta game. So then there is a unique Nash equilibrium if these are pure Kantians, they're purely moral people. So they will lend the money, they will trust, and they will honor, and so on. The expected material payoff to each player is then 3/2. So maybe that is one way to think about moral reasoning. Now, if we think of experimental data for this, I don't have any for this particular example, but trust games are pretty similar. And we know that we get something in between, some mixture. Some people do trust other people, and some people pay back and honor the trust they've been given, and so on. So it's not purely self-interested people or homo economicus, nor is it fully moral, somewhere in between. Or maybe there are other motivations. Of course, I cannot exclude that. Now, the topic that I have raised here, morality and economics, is they were quite close to each other in the old days. If you go back to economics, it was close to moral philosophy and so on, part of moral philosophy maybe even. So there were lots of discussions about connections between morality and economics in the old days. And I just give here a list of some references up to today. Adam Smith, in his book on moral sentiments, elaborated quite a lot on morality and empathy and things like that. Edgeworth, when he drew up his Edgeworth box, he mentions that, of course, he assumes in selfishness that on the contract curve, you care only what you get. But he said, of course, that is an abstraction, that in practice, people care about what is fair and what others get and so forth. So an Arrow mentions in 73 in a paper that we should actually introduce more morality. He was thinking of, I think, environmental economics and things like that. Lafont, likewise, in 75, suggested that Kantian morality is something we should try to incorporate in our thinking. And Amartya Sen, of course, has thought a lot about morality. Then there are other papers by other people mentioned here up to this day. So let me then suggest to proceed, since this is a game theory conference also, and I'm fond of game theory, see what we can do in terms of game theory for this. So here is a simple model which comes from a paper with Ingela Alger from 2013, and we have elaborated and extended since then, but consider now symmetric two-player games and finite. So it's a finite set S of pure strategies, as usual, the same for both players' roles, and let delta denote the set of mixed strategies, the simplex. And then what I will call now material payoff function will be some function pi, which takes a pair of mixed strategies and maps it to a real number as the expectation in terms of some monetary or consumption utilities or something like that, something that you can calculate for an individual. So this will be then a quadratic formula, vector X transpose times matrix A, where A is an M by M payoff matrix, and Y is a vector of the other guy. So this is the usual framework. And note here that the notation is such that this is a payoff to somebody who uses X against Y. So it doesn't say player role 1 and player role 2. It says, if I'm using X and I meet somebody who uses Y, this is my material outcome. So the other guy then gets pi of YX in the same meeting. Well, let me then define the following class of utility functions or payoff functions. I will call them utility for distinguishing them, so not mixing them up too much. So for a given kappa, a number between 0 and 1, let U kappa be a convex combination of my material payoff when I use X against Y, and what would be my material payoff if we both used X. That would then also be the other guy's material payoff. So this is a convex combination. It gives some weight to the self-interested material payoff. If I expect to meet Y, I can think of what I can expect from myself. The other one says, I don't care about what Y is. I just think about what happens if the other would use what I'm using. So if I write it in that form, then we get back both the plain vanilla Nash, so to speak, when we think of these as being the material payoffs. So selfishness or homo economicus, kappa equal to 0. So that is, I disregard the second term. while kappa equal to 1 is the extreme opposite case, when somebody doesn't care about the consequences directly, but what would be the right thing to do in the sense of Kant, as I understand, as I read Kant. And for an arbitrary kappa, Alger and I, we call these homomoralis, so they can be differing degree of morality, these guys. So this is one-dimensional family of utility functions. So it's just one parameter. Now, if we would know kappa, the degree of morality of a player, then we can figure out what are the best replies. That's beta kappa. If I expect y, what is my set of best x's? And then we can think of fixed points. So we can think of capital X kappa as those strategies that are best replies to themselves when used by people who have kappa degree of morality. So if I take a pair of points from this set, so I take x a point, any strategy there, and if it meets itself, that would be a symmetric Nash equilibrium between two homomoralis with the same degree of morality kappa. So this is the machinery, the notational framework. And please don't hesitate to interrupt me if there's any question so far. Okay, so I will ask now 3 questions essentially in this talk as my main focus. And I will be brief on the first 2 and more at length on the third. The first one, is there any empirical evidence for this creature, homomoralis? Second question, is there any theoretical foundation for it? And the third question, which is my main topic here, what about equilibrium? And this is a problem which I think is important because, Nash, when he wrote up his model, which was finite games as he wrote it, and then mixed strategies, he gained a mathematical advantage, namely that your own expected payoff is linear in your own strategy. Okay, that's an advantage mathematically and enabled an elegant existence proof. Now we risk losing that, right? Because we add also a quadratic term that I might meet myself. With probability kappa, if you like, I meet myself. So the existence now might be a problem. What do moral people do when they meet? You can wonder, about what to do. If people are very polite, maybe they are standing there both asking the other guy to go before him and so on. You can imagine situations like that. So it can be, it's not evident that it exists. So this is my main question. But let me first briefly go through the first 2 questions. So the empirical evidence is not much because it has not been much studied. There is a published paper, which I mentioned here, and there is also some other experiments with yet unpublished. I will talk about the published paper, which you can look up, a laboratory study in Zurich. Ernst Fehr and I started it. Mikael Kosfeld joined us, and then Topi Mietinen for this. We had a sequential prisoner's dilemma interaction, preceded by a fair coin toss, which would say if you are the first mover or the second mover. So the first mover had to choose between essentially cooperate and defect. The second mover would see what the first mover has done and could either then, reciprocate or do something, react to what the other guy did. Now, we used belief elicitation here. So we asked people to say what they believe is the probability that somebody they will meet will do one or the other. And we used then incentivize that. So we pay them. The closer they come to the population distribution, the more they were paid. And then we used the strategy method. So we asked them, what will you do in this role or that role? Now we toss the coin and you must do what you have said. But we didn't make any equilibrium assumptions at all. And then we analyzed this, and the main results are on the next page. We have more results, of course, but this, in summary, we looked at some alternative preference models. Homo economicus just says people are out there for the expected monetary gains in this little interaction. They were paid in money. Another one was an inequity aversion model, Fehr-Schmidt. And then there was a conditional welfare model, which was based on Rabin and Charnes model, a variation of that, and then reciprocity model also. And we had plain altruism. Becker altruism says that I care about what I get myself, and I care positively about what other people get. And then the last one is homomoralis, which I just mentioned to you. So we did this with the data we had, with some statistical methods, and we did a number of approaches. But in this approach, what we did, we counted hit rates. So what percentage of the individuals here with what they revealed as their beliefs and their actions fits into Homo economicus, 28%, and so on. You can see the numbers there. So they get higher percentages for conditional welfare and reciprocity, and you don't get so much higher from altruism. So altruism doesn't go a long way. Homo moralis goes fine, so it goes also high. Then we used a method which is called the Zelten-Krischker score, which says you should compensate models, not for the number of parameters, which we also have done in another analysis, but here we compensated for how big is the hit area. I mean, because if you have is a potential hit area, you know, if you have a model which says anything can happen, then it has a hit rate of 100%, right? And the smaller the area is, the more falsifiable is the theory and the more valuable it is. And Zelten-Krischker, they wrote up some axioms for how one can combine these two things and in a consistent way. So we used that, and then we got the scores, which are compensation for hit rate for the hit area also. And then you see Homo moralis does quite well. So this is just, yes.
Jörgen, how much
yes.
in altruism, how much weight was being placed on the other guy's payoff compared to your own?
I don't recall right now.
Equal, more, less?
No, less to the other guy, but I don't know, and it is somewhere in the data. What we did was, you know, for this exercise, we did ask, you know, what behaviors are compatible with any degree of altruism for this group of people. Then we also estimated altruism and so on, and the numbers I've come to in this and another study is it's of the order of magnitude of 0.2.
I see. Okay.
On average, but it has a wide dispersion. So some people don't care, and others are even negative. Actually, so some are spiteful. They behave as if they attach a negative weight, and some give quite a lot of weight. Homo moralis, when those estimates have been of the order of magnitude that kappa would be roughly 0.2 or something like that. Also.
Okay.
Thank you. Yeah. Thank you. So this is what we found. So I would say that there is some foundation, you know, for this kind of preference. It does. One has to be careful to discriminate it from other ones, but one can actually and see, you know, how does it do compared to other things, and that's something I think one should do more. But there is some support for it. Now, theoretical foundations one can ask also, and then I will refer very briefly here now to Maynard-Smith, Price, and then my work with Ingelager. So as you know, they defined the notion of evolutionary stability as a property of mixed or pure strategies in symmetrical and finite games. Now, what we did, we lifted that up to a higher level. So we said that people choose their strategies, but their payoff functions or utility functions, their goal functions, are selected for. So we asked them, we define then what we mean by stability of a preference, if it can be invaded in any equilibrium by some people who come in a small fraction with another preference and so on. And what we do then, we apply this to an abstract setting, but it's just evolutionary stability, but done at a higher level. And we imagine then anonymous random matching in a large population, and the matching might be uniform assortative. So it might be that when I come in there, if I'm of some type, it might be that conditional on my type, I might see more people of my own type or not. And the index of assortativity is sigma, and this is machinery which one can use. And it's Ted Bergstrom who started to write it up very elegantly, actually. So we use that, and then what we find is that it doesn't matter how we define the strategy space very much. You know, it can be pure mixed strategies. It can be the only thing we need is that the strategy space is compact and convex, and that the functions we talk about are continuous. So that's all, essentially, for this setup. And then we find that Homo moralis with a degree of morality kappa equal to the degree of assortativity is evolutionarily stable against all behaviorally distinct continuous utility functions. So you can throw in a little subpopulation of mutants who have some other continuous function, and if it's behaviorally distinct, which is what you imagine, you can, which I don't go into now because it's technical, but you can see that they behave differently. Then they will be not doing as well in terms of material payoffs, but they act upon their own subjective goals or values. So. Okay, and then we also have a result that says that if you take another utility function, which is behaviorally distinct from this one that I mentioned, it will be evolutionarily unstable. We can find then a mutant who could invade that population. Now, this result has been extended by us to n-player games that are symmetric, and it has also been corroborated in another paper, another model, which is completely different. It's a stochastic population model of the type used in genetics, and we apply it to preference evolution with Laurent Lehmann in Lausanne, and we can find results and which corroborate this. They agree with this when we specify this stochastic process in the most conventional way for genetics. So there is some theoretical support. Okay, so then I have argued that there is some empirical validity in this. Apparently, it can be, we can explore it more, and there is some theoretical foundation. So what I did then with Bomser, Schachinger, who are mathematicians in Vienna, we said, let's look at equilibrium play a little bit more carefully of these creatures. And we stay with the simplest possible setting in this new set of questions. So we do it in finite and symmetric two-player games again. And we look at two cases. One is when there is complete information between equally moral players. So you imagine a world where people have some degree of morality and everybody has that degree of morality. They walk around there. Maybe the degree of morality is 0. Then we are in the standard world of basic plain vanilla John Nash. And then it could be that they are quite moral like Kant, or they are somewhere in between, but they are of the same degree of morality. Now, that's one setting I will talk briefly about. Another setting I will talk briefly about is incomplete information. So now imagine that there is a distribution of types of different degrees of morality, and everybody who is in this population interacts with somebody else and knows his or her own degree of morality, but not of the others. The presumption is that everybody is some variety of homo moralis, but they might be of different degrees of morality. Okay, so is this clear? I'm just playing with this model a bit. So just a little bit of notation and some results. So W, I use that to denote the expected material welfare, the sum of the payoffs to the two guys, if they both would use the same strategy, because that's what Kant talks about, right? So that's twice pi of xx. That is, the material payoff I get when I use x against somebody using x, and 2 times that. That is the sum, what both players get, and we can write it as a quadratic form, as you see there. And that's why it's useful, because then we can clearly see there is a quadratic form coming in here, so we can have some convexity and concavity and indeterminacy and so on in this setting. Okay, so we start with a very simple observation, which says that, well, the set of fixed points, and symmetric Nash equilibrium, if you like, is non-empty if kappa is either 0, which is Nash's theorem, actually, to prove the existence of Nash equilibria, and this is symmetric equilibrium, which follows from that, actually. Which is easy to show with the same mathematics, or if it is like Kant said, because Kant says that you strive to maximize the welfare function, and hence it's an optimization problem, and then it follows there also that there exist fixed points, right? People don't care what other people do if they are moralists of this type. Now, then, since we saw the form of this function, if you remember, I will go back to that form. You see here up here on the line here, you see that it is a convex combination of my payoff and, if you like, this payoff, which is kappa divided by 2 times the welfare, right? This is just half of welfare. So if the welfare function is concave in x, then this is a linear in x. So then I get the concave function. If it's convex, I get the convex function, and so on. So this property is inherited for the homo moralis preference. Okay, so that this proposition just says, that if it so happens that the welfare function then material payoffs are such that W is a concave function on the simplex, well then there exists again equilibria, right, by standard fixed point theorems. So that's a little observation to start with, and then we look at some examples, and I will just mention 2 simple examples to begin with here. Coordination games. Either both players use their first pure strategies and they each get a payoff of A, which is a positive number, or they both use the second strategy, they get B, which is a positive but smaller number, or they miscoordinate and then they get 0. Now, as we well know, when morality is 0, there are 3 fixed points. To the first pure strategy, that's 1. The second pure strategy, another one, and a mixture. And the mixture is given here, X star, depending on the parameters. So that's for 0, when no morality. And then we notice W is strictly convex. which means that Homo moralis preferences are also strictly convex in its own strategy for positive kappa. And best replies are pure. Whenever you meet somebody, you want to do a pure best reply. So therefore, the mixed equilibrium vanishes. And so does the inefficient equilibrium. It also vanishes if kappa is high enough. The reason is that even if other people play the bad equilibrium, if I'm sufficiently moral, I will play what we should have done, all of us. We should play the good equilibrium. And this is then shown here. If you can see this diagram with red, there's a red line here, there's a red dot here, and the red line there. It says that as a function of kappa, what are the fixed point values of the probability given to the first strategy, of which can reach the payoff A, the higher payoff. So to play the good equilibrium is always an equilibrium for Homo moralis. To play the bad equilibrium, the coordination equilibrium, the less efficient one, is that up to a certain degree of morality, but then it ceases. The mixed equilibrium ceases to be an equilibrium as soon as you have any degree of morality. So you could say that just adding a little grain of morality knocks out the mixed equilibrium. So if you want, you can use this as a selection criterion. You can say which of our equilibria in standard models would survive if you add a little grain of morality, and this says the mixed equilibrium in coordination games will disappear. Okay, then I consider an anti-coordination game. So suppose that instead of having positive payoffs on the diagonal, and you want to do the same thing as the other guy, you want to do the opposite guy. That would be a kind of a difficult example for Kant, one would imagine, right? That my best reply is to do the other thing than the other guy is doing. So A and B are positive, and they are off the diagonal. But now W is a concave function on the simplex. So now you strictly prefer to mix if you're a moral player with positive kappa. And there is a unique equilibrium here, which is given here, x star of kappa, which generalizes the standard one, which we would get for kappa equal to 0. As players move from kappa 0 to kappa 1, the probability of playing the first strategy is increasing, and it goes at the end, you reach 50-50, because that is what maximizes welfare. So, but 50-50, randomization here gives the payoff of A and B divided by half, right? Because if I add up the payoffs, they get either 0, or one gets A and the other B, or the other way around, or 0. So this is what happens. And if they are moral, but with lower morality, for example, 0, they get a lower payoff than this. The welfare is lower. So this is how it behaves. So it doesn't mean that they are doing something good for the group, if you see what I mean, because good for the group would be something else. I also add here with the star that there are also asymmetric equilibria, even when they are Homo moralis, and we don't need to talk about them maybe right now. So I will not talk about asymmetric equilibria in this talk. So they're interesting. I also added a double star here because you might say, well, this doesn't sound a good thing to do, to play this game. If it were played by people, one would imagine in some societies you would invent some kind of public randomization device then that would assign player roles. So you toss a coin and say, you are the row player, I'm the column player. And then man can show that in that game, moral play will reach the maximal material payoff. They will coordinate. They will, sometimes play one of the off equilibria and sometimes the other one. But that goes outside this talk a little bit. Because in this given game that I gave it, you don't know if I'm called player 1 or player 2. I'm just meeting another guy. I have a strategy X in my hand. I can choose strategy X. This is what they do, and it's an equilibrium, and the payoffs are not great for these moral people. They're better than for selfish people, but not great. Okay, here's a class of games which is familiar to game theorists, zero-sum games and constant-sum games. And what happens? Well, any player who has any degree of morality below 1 behaves exactly like Homo economicus, like a self-interested player. There's no difference. So perfectly competitive games, situations with perfect competition. Immanuel Kant's, model, if we say the degree of morality is not 1, it's less than 1, it says they will behave like selfish people. And the reason is, of course, that welfare then in a constant sum game is a constant. So you only look at, and you cannot change that. So the only thing you can change is your own material benefit. So they will behave the same way, except for when we are fully Kantian. If they are fully Kantian, then they say, I only care about welfare, and welfare is a constant, because whatever we do, if we do the same thing, whatever strategy I take and the other guy takes the same, we earn the same payoff. So so then everything goes. Okay, so that's a class of games where you would not see any difference if you do experiments on constant sum games and so on. This theory says you shouldn't see any difference if people are moral or not. That's a falsifiable statement.
Jörgen,
yes?
You have 5 minutes to talk and 5 minutes.
Thank you very much.
Questions.
Thank you. Yeah, thanks. Fine. Okay, and then I have a little game here which has no equilibrium in pure strategies or mixed strategies when played between equally moral players. It's a rock, scissors, papers game, as you can see there. And as we know, for self-interested players, for standard game theories, this has a unique equilibrium, which is a mixed symmetric equilibrium, x star 0, 1/3, 1/3, 1/3. And we also know from some literature that this is unstable in the replicator dynamic if A is negative. Then the dynamic swirls out from that midpoint, and it's stable if A is positive. So let's look at the difficult case when A is negative. So then W is easy to see is strictly convex. Okay, so in that case, we have some moral players, convex welfare function. Then they want to answer, their best replies are always pure replies, right? They want to go out to the corners. And also, if you calculate, what happens if I meet somebody who has strategy 1, who is playing, if I expect strategy 1, I will play strategy 3, so I will play paper against rock. And my payoff then will be bigger than 1, and 1 would be if I responded with the same strategy as the other guy. So there is no equilibrium here. So for this example, when A is negative, there exists no fixed point. There is no symmetric Nash equilibrium between moral players here. Now, more generally than this example, one can give a condition then when is a pure strategy, a fixed point under morality? Well, it is under this condition, which essentially says that you should earn enough on the diagonal compared to off diagonal. That was essentially what the example I said. Now, these results that I've said so far, they say that if W is concave, then the existing equilibrium is strictly convex. Then we can say which vertices are equilibria and so on. But the usefulness of that depends on how easy or hard it is for us to see if a welfare function is concave or strictly convex on the unit simplex. It's not enough to say on the space, it's on the unit simplex. And for that, we have results. And I will not go through them now because of a short lack of time. So what one can do, one can characterize concavity and strict convexity by means of essentially linear algebra and a linear quadratic maximization optimization theory. So one can construct a matrix from the payoff matrix, a symmetric matrix, and if it is semi-definite, then it's concave. If it's positive definite, it is W is strictly convex. So there are machinery for these things. Okay, let me then end up with talking about incomplete information, and I think that's super important, of course, because we don't know. I don't know even my own degree of morality, if I have any, and it's hard to know what other people have, of course. So imagine now that there is a population of people, and they know their own degree of morality, but not that of their opponent, but they presume everybody is some variety of homo moralis, and let mu then be the type distribution. So that's the distribution of kappa values that you meet in a way. Okay, what is a strategy? The strategy then in standard way, it will be some function xi that for each type that I might be suggest a mixed strategy that I might play. Okay, and we say it's optimal if for every type in the type space, it assigns a mixed strategy that would be optimal for that type. Okay, so that's the natural extension, I think. And then one can show that there exist measurable selections from these. So these strategies do exist, the optimal strategies do exist. And one can then use that to define Nash equilibrium. So simply a strategy now, which says, if I'm this type, what do I want to do? That's the best reply to itself, or a symmetric equilibrium, if you like, under incomplete information, if it satisfies the equation 2 there, which says that for every kappa, I should do what's optimal for that type, under my expectation that I'm meeting somebody who uses the same strategic psi, right? And then we see something very nice here, I think, and that is that the function u kappa, the maximum there, is the simple, bilinear form. So it is actually linear in the second argument. Like Nash used it for the first argument, here we can use it for the second argument, say that the second is linear there, so therefore we can integrate into the function. So we say that the integral that I have there, the integral, can be written simply as uk of x and replacing then psi tau by its mean value. So it's simply that function, right? uk of, if I use x against the mean agent, so it is as if I need to check if this can be a Nash equilibrium, is it optimal against the representative agent for the population's mixed strategy, which makes it mathematically more manageable. Okay, so now existence of Nash equilibrium is still non-trivial, but we do have a characterizational result in terms of first and second order conditions, where we can say if and only if a given strategy is best reply to itself. And I will skip that. Okay, so that there is machinery here, and one can then say there is an existence problem, one can handle it, and one can at least characterize in many games, what is an equilibrium, and if they have equilibria, but we don't have a full answer to all the questions we would like to ask, I would say. Now, in the conclusion then, I hope that I've shown you that the different approaches by Nash and Kant, they are different, surely, but one can reconcile them and combine them using game theory. And I think that's important because I think moral reasoning is very natural for humans. And I think that lies behind when people motivate what they do, when you read after experiments and so on, why do you do this and so on. One type of reasoning you find there is that seems to be the right thing to do and so on. So I think that matters. And I hope I've given answers
Jörgen, if you want to
questions. Yes, yes, please.
Sorry. So if you want to answer questions, then that's the time.
Yeah, I now will answer here.
Yeah.
I will stop here, and I will say that these are some answers to some questions, and there are many more interesting, fun, and challenging questions remain. And you're all very welcome to join in on this, I find, exciting research agenda. Thank you.
Thank you, Jörgen.
I have
Any questions?
Clarification. You probably said this, but I missed it. When you check for stability,
yes,
when you check for k = 1, whether it is stable, the mutants can be all possible k's less than 1 and other things.
They can be any function at all, any utility function at all. No, there is no restriction to this family. So we ask, does there exist any continuous function of the product space of strategy profile of profiles that could invade? So it can be any crazy function.
I see. Thank you.
So this is full function space, infinite dimensional.
Thank you.
Any other question? So let me ask a question.
Yes.
I'm used to thinking population games about randomization as everybody plays a pure strategy, and it's just that half of the population play this and half of the population play that. This works well with Nash, but how does it work with this Kantian reasoning? Like it seems like it's not moral to play a pure strategy.
In this setup, as you're absolutely right, this suggests that in some games, players have a strict preference for randomization. So that follows from this, if you have a concave welfare function, you strictly prefer to mix. That's correct.
So
I agree with you that, with Nash, and that is a very pretty thing with Nash, the mass action interpretation, we can think of mixed strategies as actually, they are not, people don't need to mix, but there is a large population and some do one thing and some do something else. And the mixed strategy is just statistics for the different strategies.
But here we need to randomize. Okay, we have one more quick question, I think, from Francisco. the solution concept is label dependent.
I'm sorry,
Is
it is what?
True also? Is label dependent? You could also look at the question yourself in the question and answer.
I'm sorry.
Is this true also for some other social preferences that were presented? I'm not sure I understood, but
I'm not sure I understand the question. Let's see if I can see the question. I don't know what it means, label dependent. What I might want to emphasize, which might have to do with the question, and then maybe I can get the question again, is that what this does, it asks about a strategy that you use yourself and against some other strategy. And it does not condition on if I'm called player 1 or player 2. So it's not labeled in that sense. If two people meet in a symmetric game, and this is then in the population literature, the same thing, like Maynard Smith and so on, right? If you say that we call you player 1 and you player 2, then I say that's fine, but that's then a game where first nature tosses a coin and then tells me I'm player 1 or player 2. Then I get the label, and then I get the game again, which is again symmetric in the same sense, and I look for the same set of solutions. So,
okay,
I don't know if I understood the question, but
also offline. Okay, thanks, Jörgen.